Hi everyone, thanks for checking out this video. This is going to be a lesson about how to fit distributions to data in R. And if you guys have been watching my recent videos, you might know that I've been making a lot of R videos recently. That's because my new job that I started recently is a lot of R programming. So I'm partly making these for my own benefit to force myself to learn more of the R language. But then I was also thinking that the topics I've previously covered in Python that people found helpful, I'll try to also cover those topics in R, and maybe people will also find those R videos helpful. So this is going to be a repeat of a topic I already covered in Python, but now I'm going to show how to do it in R, and basically how to take some data that you think is following a certain kind of distribution, and how to estimate the parameters for the distribution fit in R, basically. Okay. So I'm going to show three examples. So one is going to be kind of like the most basic fitting you might be doing, just fitting a normal distribution to data. The second one is going to be fitting a non-normal continuous distribution to data. And then the third one is going to be fitting a discrete distribution, which is another type of distribution that's not continuous but discrete. That'll be the third example. Okay, so for the first example, I made up this fake data set called diner quality. So this is like kind of what I think is the quality of diner restaurants. I think most diner restaurants are like kind of okay, and some of them are kind of bad, and some of them are kind of good. And the whole distribution, I'd say, is like kind of this like normal looking bell curve, like Gaussian distribution. I'd say this is like what I think of like diner restaurant quality. And so we're going to use this data set as an example to fit a normal distribution to. Yeah, so I have this plot here, and then I also I called it a CSV, but really there's not any commas because there's only one column of data. So it's basically like in this CSV file, it's like every line is the rating of a different diner restaurant on this kind of like unitless scale. But yeah, every line is just a different score of a restaurant, basically. Okay, so I'm going to show you guys how to fit a normal distribution to this data in R. So hopefully this will be pretty easy. I think it's easier to do in R compared to Python, so hopefully it'll be pretty easy. So yeah, I just start off like usual with all of my R files. This line just clears your current environment, so I always run that just to like clear out the current environment, clear any variables we have already. Yeah, then you're going to need this library called the mass library. I think this comes with R. If you don't have it installed, it's just install packages. But I think it comes with R automatically, so you should have it already. But yeah, just make sure you can load that in. And then, okay, so I'm going to do in the same script all three of the different examples. So I'll kind of put like a little block here, and then just a comment, normal distribution. Okay, and then the first thing to do is just read in the data. Oh, also make sure you have your working directory set up properly. So my working directory here is called R practice, and then yeah, just like set that as your working directory so that you can read in the file properly. And then yeah, I'm gonna be a little bit lazy here, just copy and paste a little bit of code just to read in the CSV. So yeah, just read.csv and then the path to the CSV, and then the CSV, the way I wrote it, it doesn't have a row for like the column name. It just starts off with the data. So if it had been something like where you have the name of the column, then you would not have this line here. But since there's no column name, I wanted to just let R know that there's no heading at all. So I just put header equals 0, so that it knows to like start with this first row immediately reading in the data. And yeah, so we read that in 10,000 observations, 10,000 data points we have here. Okay, so it looks like it read in properly. The next thing to do is we need to, like right now, this is a data frame. I'll show you guys what it looks like. I mean, not what it looks like, but what the class is. Oops, sorry. But yeah, it's a data frame. We need to cast it into a numeric vector. So I'm going to say data, this arrow equals unlist s vector data. And then now we have it as a numeric vector. We just need to get it to that numeric vector just to be able to use this distribution fitting tool. Okay, and then the actual code for fitting the distribution is very, very easy once we have this library read in. So we're just going to say fit arrow equals fit. Fit dist r, like for distribution, data, and then normal. And you guys are going to see when we do the next couple examples, we can make this a bunch of different kinds of predefined distributions. But for now, we're just going to make the normal distribution. Okay, run that. Yeah, so this gives us our fit parameters for the normal distribution. So you guys can also like look up for whatever distribution you're working with, just like look up what the distribution is and like what the different parameters mean. So for the regular, just normal Gaussian distribution, there's two parameters. There's the mean and the standard deviation, and that's what we got out of this fit here. We have the fit mean and the fit standard deviation. Yeah, so that's what we get for the fit. And then we can like unpack these if we want to. We can say like mean fit arrow equals fit $. Remember, this is how we like unpack these variables in R, and then we can say $, estimate, and then mean. That should give us the fit mean here. Just make sure that worked okay. Yep. And then we can also say standard deviation fit. Do the same thing for ST, standard deviation. Okay, so yeah, now we have our fit. Now I'm going to show you guys how to plot the histogram of the data first before we plot the fit line. Show you guys just how to plot the actual distribution of the data that we read in. I'm going to be a little bit lazy, just copy and paste the code here. Yeah, but pretty simple, just using the hist command here, and then just plugging in our data. We can like make the columns whatever color we want. This is like the title of the distribution, like an x-axis label and a y-axis label. Yeah, so that's our plot for our distribution that we read in. We can like check and make sure that it's the same as this. And yeah, it is the same data. The only difference is the binning is different. I put like 20 bins in here. This had many more bins. Sorry about that. Had a little bit of confusion for a second there, but yeah, as I was saying, you guys could, like, I made it 20 here. The only reason it looks a little bit different is because I think this was something more like 100 bins or something. So you guys could also make it like 100 bins in here. Then it would look a little bit more like this actual plot that I made. But yeah, I mean, this is just for visualization. I'll just for now just make it 20. I think that's fine. And then to actually plot the fit distribution, I'm going to be a little bit lazy here and just copy and paste in some code. And actually, to be honest, this is code I got from ChatGPT. I've been finding ChatGPT like very, very useful for stuff like this, like plotting and stuff. I still don't exactly trust ChatGPT for like more complicated analysis. For like more advanced topics, but I've been finding it super useful for like making plots and stuff, especially learning a new language, learning R for the first time. So yeah, I actually got this code for plotting the fit line from ChatGPT. So I recommend you guys to check that out too. So yeah, rather than explain all of this, I'll just kind of leave it up here so that you guys can copy it to. Whoops. Sorry about that. I think I just I called these things slightly different things here. So this should be, rather than mean estimate, I think I called it, yeah, mean fit. So I'll just yeah, plug that in there, and then standard deviation fit. Yeah. So sorry, I'm not going to explain like exactly everything that this code is all doing here. To be honest, yes, like I said, I don't think it really even makes sense to be like memorizing this kind of like plotting syntax, because this is something that has like already been kind of replaced by ChatGPT, where I think it just makes sense to just use ChatGPT for this application. But yeah, so now we can plot our distribution and then the fit line over it. Whoops, I think this actually, if we want to keep our same binning as before, I think we need to put this breaks down here too, I think. Yeah. So yeah, just be careful about that. Just if you're doing another hist down here, just make sure you're putting in again whatever you want your breaks to be. But yeah, so that's how we do it for the normal distribution. Yes, like I said, R makes it very easy. It's a lot easier, I think, in R than in Python. Yeah, R is very good for this kind of work. And yeah, I recommend you guys just don't worry about like memorizing this kind of like plotting syntax. You guys can just kind of like copy it or just use ChatGPT to get it. Um, but yeah, the important part here was really like these couple lines. This is how we actually do the fit. We can use this function here for a bunch of different distributions, like I'm going to show you guys in the next couple examples. But yeah, this is the important part here, where we actually fit the distribution to the data and then unpack our fit parameters that it gives us. Okay, so let's try another example. Let's try now. I'm going to show you guys an example where we're going to be fitting a log normal distribution. So that's another kind of continuous distribution, similar to the normal distribution, but kind of a different shape to it. Yeah, so I'll show you guys the example I have for that. So I made up this other data set called pizza shop quality. So this is what I think is like the quality of different pizza shops. I think most pizza shops like mostly are kind of bad, but then occasionally you find some kind of good ones that kind of stand out. So that's why I made this distribution kind of more heavy on the left side, heavy on the like worst quality side. But then it's got this like tail where you kind of get better and better pizza shops that get like more rare and like more rare, I guess. But yeah. So again, just an example. And then yeah, I made up this CSV yeah, pizza shop quality. And it's the same idea, just every line is like a score for a specific pizza shop. And yeah, so we can really use like almost exactly the same code that we use for the normal distribution. I'm just going to like repeat to just show you guys that we can do other stuff like other non-normal distributions. So I'm going to read in this pizza, whoops, shop quality. Oh, sorry. Maybe before we ever do that, I'll just clear the workspace and reload this library. And then yeah, now I can read in pizza shop quality. Yeah, 10,000 observations. Just like what we wanted. Then again, cast this to a numeric vector, because when it gets read in, it's a data frame by default. So we want it to be a numeric vector. Okay, again, can do mostly just copy and pasting here. Yeah, for this part, it's the same command, except it's going to be log normal, and then yeah, it does the fitting automatically for us. Then we can look at what we get for the fit, and then yeah, it's got two parameters, except it's yeah, like the mean log and the standard deviation log. Again, it's like similar to the normal fit. It just fits automatically the parameters, and then we can unpack them. Yeah, we can unpack them with the same kind of code here. So I'll say yeah, mean log fit and standard deviation log fit, and then yeah, just mean log and SD log. And yeah, okay. Looks like we're all good so far. And then yeah, for the plotting, yep, plotting, same thing. Still all good, just copy and pasting so far. Yeah, and again, you can change this to be like however many bins you want it to be. Make it 100. It'll look more like the actual plot out here. And yeah, you know what? Maybe for this plot, maybe I'll just leave it 100. Um, and again, I'm going to be a little bit lazy here and just copy and paste in some code for the plotting. Um, yeah, just be a little bit careful here because this code is a little bit different from up here. And you know what? I think I need to again change these names of these variables here. Yeah, let's see if this worked okay. Yep. Yeah, just be careful because some of these things are a little bit different than the previous code up here. Again, I got this also from ChatGPT, so you guys can just copy it from my code if you want to, or just use ChatGPT yourself. I think ChatGPT is like, yeah, again, very useful for this kind of like plotting, especially in languages that you're not like that great at yet. But yeah, just make sure you change like up here. It was D norm. That's how we're getting the fit points for the normal distribution. Down here, it's DL norm. So again, this is how you, if you want to like plug in some distribution parameters and get the value of the fit function, yeah, you use like D norm for the normal distribution, and then DL norm. Okay, so that's the log normal distribution. That's another type of continuous distribution that isn't normal. Next, and like lastly, we're going to do an example of a discrete distribution. So for this, I'm gonna use the Poisson distribution. Okay, so before I show you guys the data set for this, I'll just kind of remind you what the Poisson distribution is. So the Poisson distribution is a distribution for basically counting the number of random events that occur within a given period of time or within a given like location. So it's really, yeah, it's about like counting the number of occurrences of events, yeah, within like a fixed interval of space or time. That's kind of, yeah, the definition down here. Yeah, probability of a given number of events occurring in a fixed interval of time or space. If the events are occurring with like a constant mean rate and independently of the time of the last event. That's kind of the technical definition. Just as like a way of remembering it, I just think about it as like counting the occurrences of an event that's happening randomly, but with a constant underlying probability. So the fake data set I made up to make it kind of realistic is the number of customers per day. So if you have a restaurant and you're keeping track of the number of customers you have per day, that's an example of a possible use case for fitting a Poisson distribution. If you're just like counting the number of customers that happen to come in, assuming that there's some kind of like underlying like rate to it, but that like day to day it's kind of random. Yeah, that's an example of when you could use a Poisson distribution. So yeah, I made up this fake data set, customers per day. And again, it looks the same, except you guys might notice they're integers because it's a discrete distribution. I mean, technically, discrete doesn't have to be integers. It could be discrete floating point numbers too. But yeah, it's not a continuous distribution like these other ones were. It's just discrete numbers of customers that you can have on a given day. But yeah, again, it's like each line is a different data point. So yeah, we can treat this kind of largely the same as we've done the previous two examples, except the only difference is going to be there's going to be a little bit of difference when it comes to plotting the results. But yeah, we'll get there in a second. So again, just clear the environment, load in the library, and then you can copy and paste a lot of this code. Say copy and paste customers per day. You can read that in. Oh yeah, this one I made it not as many observations rather than 10,000. I just made it 1,000. But yeah, other than that, it's kind of the same. We have to just cast the data frame to a numeric vector, and then we can do the fit. Before I do this, I'll just show you guys that if you guys are being clever and really remembering like the properties of your distributions, if you guys are clever about this, you might realize that you don't even, for the Poisson distribution, you don't even have to do this like fancy kind of fitting, because the Poisson distribution only has one parameter, and the only parameter is the mean. So if you guys are being clever, you might realize you don't even have to do this like fancy function. Like the fit of this parameter is just the mean of the data if you're dealing with a Poisson distribution. This is going to be the fit parameter because the Poisson distribution only has one parameter, and that parameter is equal to both the mean and the variance. Yeah, it's equal to the mean and the variance. That's the only parameter. So if you just take the mean of your data, that is the only parameter you need to fit. So you don't even have to do this like fancy like fitting with this function here. You can just take the mean of the data and say that's your parameter lambda. But I'm going to show you guys how to do it with this function anyway, because using this function, you can do other kinds of discrete distributions besides the Poisson. So I think it's still useful, even though it's simpler to just take the mean of the data. I think it's useful to know how to use this function here, because you can use it for like other kinds of distributions besides the Poisson distribution. So I'll show you guys how to do it here. Yeah, fit. Look at the results and notice that our fit is basically the same as just taking the mean. So it just yeah, like I said, this parameter lambda is equal to the mean of the fit distribution and the variance. So we could have just taken the mean and that would have been it. But if we want, we can also use this fitting function and get the parameter that way. Yeah, and then from there we can unpack and say, lambda fit arrow equals fit estimate lambda to kind of unpack here, and then I'm gonna show you guys again how to do the plot of the histogram here. Yep, you guys can see it's it's discrete. So yeah, it looks a little bit different than the continuous distributions, because each one of these is the count like for a specific number. Yep. And then again, I'm just going to copy and paste a little bit of code. It's going to look a little bit different for the discrete fit. But yeah, I just got this from ChatGPT, and I recommend you guys do the same. This is how you plot the fit points for the fit Poisson distribution. Whoops, called a different thing here. Called it lambda fit. And yeah, you might see it's plotting dots here. Again, that's just because it's not continuous. It's a discrete distribution. So yeah, you just plot it differently. You plot it with the dots for each of the possible counts you might be seeing. But yeah, these dots here are showing our plot of the fit distribution, and we can see it matches reasonably close to the actual distribution of the data. Yeah, so that's how you do it. From here, you guys could like export this as a PDF if you want to, or just report like the fit parameter value. And yeah, again, this library is nice. Yes, library, because you can use the same exact line. You can use this for a lot of different distributions, and it's like pretty much the same syntax for like all of them, whether it's continuous or discrete. Just plug in your data vector, give it the name of the distribution you want to use. Can do it for a lot of them, and then it gives you all the fit parameters that you can then unpack using this kind of syntax. But yeah, again, just to reiterate, it's nice that R makes this pretty easy, makes it a lot easier than Python. If you guys want to download these data sets and also download the code, it'll be up on my GitHub. I'll put a link in the description to my my GitHub page. You can find the data and the code there. Any questions, just let me know in the comments and I'll try to answer them. But yeah, thanks for watching, guys, and see you next time.